And the ice table, it is based on the reaction stoichiometry. So the reaction stoichiometry, we make a table, and this table, we list all the quantities, the moles of each reactant and product. And before the reaction begins, we will have the initial amount of all the reactant and product in the system. So because we are discussing the equilibrium, and so at the beginning of the reaction, there may be some product already existing in the equilibrium. And then we look at the change. We look at the change of each reactant and product. And then if we know the change, then we will know the equilibrium, at equilibrium, the amount of each reactant and product. And that's the ice table. The ice table is based on the reaction stoichiometry. And the ice table, or the reaction table or solution table, some of them call it a solution table. It consists of a balance equation. So there'll be coefficient for each reactant and product. And you'll be given the initial quantities of the reactant and products. So how many mole each reactant and product before the reaction begins. And this table and also shows us the changes in those among those reactant and product. The changes is a C, okay? Initial is I. And once the reaction reaches equilibrium, the change will stop. There'll be no more further changes. But compared with the initial and the final, there's a change. And change in physical science, delta, which is change, always use the final minus initial. And for equilibrium, the final is the equilibrium state. It is when the reaction reaches the point, the forward reaction rate equals reverse reaction rate. And change equals equilibrium or the final minus initial. And so that's what the reaction table looks like. And let's see some examples. This example is nitrogen gas reacted with the 3-chlorine gas and give you nitrogen trichloride. So let's say we have a hypothetical situation. And in the beginning, before the reaction begins, we already have the reactant and some product mixed together. And these, suppose, let's say we have, in terms of molecules, we have 100 N2 molecules and 200 chlorine molecules and 50 nitrogen trichloride molecules. So these are the amount of in molecules. And after a while, once the reaction, suppose, reach equilibrium, and we take a look at the system again, and we find out the nitrogen now have only 90 molecules. 90 molecules. What about the others? What about the rest of the table? Can we find out? Well, so if you look at the what happened in this reaction, this hypothetical reaction, what happened with the nitrogen is the nitrogen, the number of molecules decreased by 10. There are 10 N2 molecules reacted with the chlorine molecules and produce nitrogen trichloride. So if there are 10 molecules reacted, 10 molecules reacted, every one molecule, based on the balance equation, every one N2 molecule reacted with 3 chlorine molecules. So now you have 10 molecules reacted, 10 N2 molecules reacted. There should be 30 CO2 molecules reacted. And also the every 1 N2 reacted with 3 CO2 produce 2 NCl3 molecule. Now you have 10 molecules reacted with 30. The NCl3 molecule gain, it should be 20, because that's what a balance equation is for. Balance equation shows us how many reactant molecules should react, what's the ratio between the reactant molecules, and how much accordingly, proportionally, the gaining, the increase in the product. So if you look to find out a change, figure a change, change is equilibrium, the end minus initial. And so the change for the N2 is 90 minus 100. Change is negative 10. Okay, because change, it is end minus initial. And so we have 10 N2 molecules reacted. Based on the equation, the coefficients 1 and 3, every 1 N2 will react with 3 CO2 and produce, gain 2 nitrogen trichloride. So if there's 10 N2 molecules reacted, the number of chlorine molecules react should be proportionally 3 times as much. 30 chlorine molecules react. And the gaining, okay, this is product. When you lose a reactant, the product will gain. The gain, it is the coefficient times 10. Gain 20 nitrogen trichloride molecule. So the ratio, the proportion, you can see the proportion, 1 to 3. And then, if you don't look at the sign, it is 3, it is 2, by twice as much. The ratio among the reactant and product exactly as given as the balanced equation. Okay. So that's what the equation gives us. If it's a 10 N2 molecule react, it must react with 30 CO2 molecules. And meanwhile, it produces 20. Because when we lose the N2 molecule and lose the chlorine molecule, those atoms will still exist, but they are existing in a different form. It is in the product, in a completely different format. And so the change, we start from find out the change of the run reactant or product. We can find out the change for all the others because change is based on the same proportion as the balanced equation. Okay. Now we figure out all the changes. Any questions? Are we following and understand how those changes taking place? It is given by the balance equation. When we lose a reactant, we are gaining in the product because of conservation of the atoms. The total number of atoms of each element should be the same before and after reaction. Okay, so what happened to the end? What about the equilibrium for chlorine, the CO2? Well, this equation change equals the equilibrium or the end or the final minus the initial. If I rearrange it, the equilibrium should equals I plus C. E equals I plus C. Or make it look more nice. I plus C equals E. That's what I is for. The ICE table, it means initial change and the equilibrium or end. And also means I plus C equals E. Initial plus change equals end. So we're asking, we're trying to find out what's the end for chlorine. The end of a chlorine or the equilibrium of a chlorine, it is the initial plus the change. That'll give me 170. The end of a chlorine gas, it has 170 molecules. And the nitrogen trichloride, the same thing. Initial, which is 50, plus change. Change is positive 20 because we're gaining the product. Okay, so after that, we get a 70 nitrogen trichloride molecule in the end. And does this one make sense? If you look at the nitrogen molecule N2, we lost 10 N2 molecules. And how much we lost in the chlorine? Start from 200, become 170. So we lost 30. Okay. Then the number of the reactant lost, it is a proportional, follow the same proportion as a balance equation. The equations of 1 and 2 react with 3 chlorine. So when we lose the reactant, we follow the same ratio. For every 1 and 2 molecules lost, disappearing in the reactant, we lost 3 times as much as the chlorine molecules. Okay. And what happened to those atoms, nitrogen atoms, chlorine atoms? They appeared, they rebound, form, become product. And the NCO3 molecule gained by 20, and in the end becomes more than the beginning. So that's what is the basic ice table. The ratio of changes, it depends on the balance equation, the coefficient. And also for the reactant, change is negative. You can see both reactant change negative. The product gaining is positive. It is because conservation of the atoms. Each element has to be conserved. There should be no atom disappear or no atom being created during the chemical reaction. Maybe in nuclear reaction, but not in chemical reaction. So what about the general idea for this reaction? Let's say this is some other situation. All these are in mole. It can also be in molarity, mole over liter, because typical situation for a chemical equilibrium reaction, it is a container sealed with all the reactant, all the product in the same pot. There may be changes amount of reactant versus product, but everything stay in the same volume, stay in the same system. So if you start from mole and divide it by the same volume, then we get a molarity for each. The whole table, last example we start with, explain it using the molecules. Molecules makes it more easy to imagine. But if the molecule divided by the Avogadro number, then you get a mole. And with mole, you divide by the same volume, then you have the molarity. The ice table in the future, it will be all in molarity, in mole per liter, which is based on the constant volume, the chemical reaction in the constant volume. When the reaction is in the constant volume, then the when we have the mole set up the ice table, divided by same volume becomes molarity. Okay, so ice table is start from molecules, but applies to moles. In the future, the ice table is based on molarity and follow exactly same principle as we discussed, based on number of molecules. Okay, and so the ice table in the future, when you have a reaction like this, and coefficient it is 1, 3, and 2. The change, it should be proportional to the coefficient. The N2 coefficient is 1. So if the change is negative x, some unknown variable, negative x, then the Cl2 with the coefficient 3 times as much, the change for Cl2 will be 3 times as much as the N2, 3 times x. And then product, because when we're losing the reactant, the change in the reactant negative x or negative 3x, in the product gaining, it is positive. And how much the change, it depends on how big the coefficient. This coefficient 2. This coefficient is twice as much as coefficient 1. So the change is also twice as much as that change in the first reactant. So the change for general situations, especially some question, we need to find out a change. We don't know the change. We only know the initial amount, and we know the equilibrium constant. How do we know the change? We have to solve it. We have to solve the equation to find out change. So this is the key. This is actually the key. Understand the change. And this is a generic formula for the change. It depends on the coefficient. Coefficient determines the amount of change. Okay, can we find the equilibrium concentration or the equilibrium amount for each reactant and product? We apply the same as we just mentioned before. ice table, it is I plus C equals E. So which means for each reactant or product, the equilibrium amount, it should be the initial amount plus a change. We can get the final. So the equilibrium for the N2, it is the initial amount plus a change, which is negative X. This is how much at the equilibrium amount. And the same with the chlorine gas. The chlorine gas, we start with 2.00, change negative 3x, so minus 3x, and that'll be the equilibrium amount for chlorine. And finally, with the nitrogen trichloride, even though the product it follows the same way. The initial is 0.50, changes plus 2x, so plus 2x, and that'll be the expression, the mathematical expression for each reactant and product. So this is about the ice table. The key is about use the balance equation, the coefficient, and the change. The change, it is proportional to the coefficient. And with that being set, we can easily find out the equilibrium concentration. So these are the equilibrium concentration. So this is ice table, and we'll see the two situations in this chapter where we use ice table. The first situation is you'll be given the initial amount of all the reactant and product, and you'll be given the end. So that situation will be similar as this first scenario. We have the beginning, we have one of the reactant we know, and then we can find out change for each and every reactant and product, and then finally solve the equilibrium concentration for everything, for all the other reactant and product. So this is given the initial and one of the final. You can solve the ice table. The other one is a little trickier, the harder. The other one is you'll be given the initial amount of each reactant and product, and you'll be given the equilibrium constant. And based on the constant, we can set up equation to solve the X. And once you solve the X, you can solve all the concentration of the all the reactant and product. So the two situations, we use ice table in this chapter and all the following, in all the following chapters.
Professor?
Yes.
Something that I'm still kind of confused.
Yes. Yes. How determine the sign of each reactant and product? Regardless of the sign of the X, which is we solve later, the reactant, we always use negative. Because suppose the reaction is a reactant, they are supposed to diminish. And meanwhile, the product should increase. So regardless of what you solve the X, by the way, when you solve can be positive or negative. But when we designate a sign for the changes, reactant, we use negative, both. And how much negative? That depends on coefficient. This is coefficient 1. This is coefficient 3. And therefore, the coefficient for the X, it is 1x. This makes 1x.
Professor, so does that mean that reactants will always be negative? Because in an equilibrium reaction, can it go either way? Like the products go back to the reactants as well?
Well, when we set up, actually it doesn't matter, actually. Just make sure the reactant and the product have opposite sign. That's very important. It doesn't, if you like to put, okay, if you put the, let's say I want to change, let me change a different color, that we can make the, erase everything. Kind of messy. Okay, so let's say if you like to put a positive sign for the reactant, that's okay. Okay, suppose the first reactant, you notice this coefficient 1. For convenience, very important, you want to pick the reactant that has coefficient 1 as the 1x change, and that was easy to find out all the changes for the other reactant. So let's say you wanted this N2 changes positive x, that's okay. And keep in mind the chlorine change should be 3 times as much. They both are reactant, they must have the same sign. That's very important. That's fine. Okay, but in doing that, realize the product, every time you reactant gain, then the product has to lose. So the change in reactant must be negative 2x. If you keep the reactant change as positive, then the product change must be the negative. Does this kind of make sense? This is perfectly fine. If you just like what I wrote down the green, that's perfectly fine. And you solve the x will be just opposite as you said that the change is negative x. It doesn't matter. The final result should be the same. You can settle an equation like this, and in the end, equilibrium concentration is still the same. It's just mathematical. Math can't tell lie. Math is very fair. It won't be biased. Will not give you preference for one way and over the other ways. But if you, as a routine, reactant we keep the change negative because the reactant is supposed to diminish. The reason for the reversible reactions, it actually does not make much sense if you emphasize which one is reactant, which one product, because the reversible reaction, chemical equilibrium, the species in the reaction can be both reactant and product. It depends on which way you look at this. You look from left to right, then the left is a reactant. If you look from the product, from the right hand, reverse back to the reactant, then the product becomes reactant. So does this kind of answer your question? Sort of. Okay, let's say, but if you, like I said, the reactant, because they were losing reactant, then the other reactant should be same, should have the same sign. And the amount, it depends on the ratio between the coefficient. The coefficient ratio is 1 to 3. And if you set the change for the coefficient 1 being negative 1x, then the reactant with the coefficient 3 change will be negative 3x. Kind of makes sense? And the product will be positive 2x. Yeah. So either way, you solve the same answer. Your x may be not the same answer, it will be opposite. But your final equilibrium concentration is exactly the same. It doesn't matter how you set up x. Your final equilibrium concentration is still the same because you have the same equilibrium constant. Equilibrium constant will not change. Equilibrium constant only depends on temperature and nothing to do with concentration. It doesn't matter you start from pure reactant or you start with just a whole bunch of product, no reactant. It doesn't matter. The K is the same number. So the key is reactant as a tradition, for convenience, we set up as negative change. And the product, accordingly, will be the positive change. The amount of change, the ratio or the coefficient for the x, depends on the coefficient in the balance equation. Okay. So let's see the next example. This is a generic reaction. And then we see this kind of reaction in the chemical kinetics. And we have equation in the first chapter at the beginning of the semester. And anyway, this is actually related to that. The lowercase are the coefficient, and these are the coefficients, the A, B, the lowercase a, b, c, d. The change depends on coefficient. Let's say this coefficient is just a random number a. And as a convention, as a tradition, we set as a negative x. How much negative x? It is a coefficient matters. Negative ax. And for the reactant B, the change will be A and B both reactant, so they should have the same sign. This should also be negative because another reactant. The amount, coefficient times the x. And both are A and B the reactants, so both are negative changes, negative x times some number. The C and D both are products, so the change is positive, is gaining. And the coefficient C, so this coefficient times the x. And for the same last product, the same thing, plus D times x. So that's for a generic reaction, how the changes will be. And if you figure out the change, set up the formula for change, you can easily write down your equilibrium concentration. For A, that should be the initial process change, and same with this initial process change. And then for the product, same thing, the initial concentration plus the change, and so forth for the D. So that's basically the ice table, how we set up ice table. Why there is change? Because change, how much change, it depends on the coefficient. In the first chapter, in the chemical kinetics, we realize if in the balance equation, one reactant or product have a higher large coefficient, that means the changes will be much larger, If the coefficient is very small, then the change will be small. Just because nature of a chemical reaction, the atoms just rebound, form a new bond, and it will disappear from the reactant, then it'll gain in the product, and vice versa. So that's the general table, and this is basically the E. It is I plus C, or ice, or the ice table means I plus C equals E. This is very important because in the end, how we set up equation, how do we know the amount of equilibrium concentration for each reactant product? This is we find out if we know the change, or if we can solve the change, we can eventually find out the equilibrium concentration. Any questions? Okay, let's see some examples. This is actually, it should be in my video. I think my video finally explained that. This is the first application. You were given with the initial amount for all the reactant and product, and you know the change for one of the reactant or product. You can find out the change for that reactant or product, and then you find the change for all the others. Finally solve the equilibrium constant. And so the setup ice table, it is we start with evacuated empty flask, 2.00 liters, and we were given the amount, mole of HI. HI is a reactant. You can see this is a reactant. And hydrogen gas is one of the product. And then I2 is in the equation, but it's not mentioned. So we assume I2 was not there, was not been provided in the beginning. So it must be 0 in the beginning. And at a certain temperature, and we find out equilibrium, the molarity of XY. So the concentration of this is given 0.078 molar. Let's find out the equilibrium constant Kc. If you look at the question, the end, you have the molarity for HI. Ice table, it is based on the number of molecules, which in turn means it is based on mole. But in reality, the reaction happens in the container that is a fixed volume. It's a fixed volume. So the mole in the entire table, in the ice table, each mole divided by the same volume becomes molarity. And so the ice table, we should use molarity setup. And the HI, we were given the mole, H2 gas, we also have mole. We don't have molarity yet, so we need to find the molarity for both. That's where we start from. HI in the beginning, so let's mark this as the initial I. Initial, or you put in 0. Okay. And before the reaction starts, we have 0.200 mole HI, and we have the volume 2.00. So you use the 0.200 divided by volume, you get the molarity. So you have a 0.100, that's initial concentration of the HI. And with H2 gas, you do the exact same. Initial amount of H2. And that should be the mole divided by the same 2.00 liters. So you get 0.010 m. That's the molarity for H2 gas. And now you can set up an ice table and use the balance equation. The state actually doesn't matter because all these states are gas. There's no solid or liquid. So all of them should show up in the equilibrium expression. Okay, so the ice table have I, C, and E. The initial use molarity, and the HI initial is 0.100. H2 hydrogen gas initial 0.010. I2 is not mentioned, so assume the 0. And change, the change, well, so far we don't know. We need to solve it. Okay.
Well,
the questions?
Yeah. So when you say that they all show up on the ice table because they're all gas, what is a situation where something won't show up?
Yes, when you have a, well, the ice table, everyone should show up, but in the calculation, not everyone will need to show up because pure liquid or pure solid, their concentration is constant. They don't show up in the K or Q calculation, but they're still in the ice table. The ice table is very fair. Everything getting involved in the reaction, they should either gain or lose. So everything will show up in the ice table, but not all of them will be in the final equation. In the equation, it has to be the aqueous or gas. It cannot be the solid or liquid. That's the last time we went over this one. Yeah.
Okay.
Yeah. Okay, so what about change? This is the key. Coefficient 2, and this is a reactant. Let's make it a negative 2x. Because coefficient 2, negative 2x. And the reactant, so negative 2x. And H2 and I2 both are products, so the gain coefficient is 1, so just plus x. This is also coefficient 1, so plus x also. And then the end we can just the initial plus the change. That's the equilibrium. That's the end of the reaction. And for the H2 is same thing. I2 0 plus x, so in the end is x. Okay, can we solve the x? We don't have the Kc, the equilibrium constant. Okay, but we have the equilibrium concentration for HI. This is actually given, which is this. So the equilibrium concentration for HI, we have the mathematical formula, and we also have the value. So that's actually where we can solve the x. This is a mathematical equation, the formula for the equilibrium concentration for HI. This is the actual amount. you can solve the x from here. Do some rearranging. You basically move the 2x to the right and shuffling. Anyway, you guys know how to solve the equation. I will not repeat how exactly solve. The x should be 0.011. That is x. You need to solve. And once you solve, then the whole ice table is solved because the H2, for example, H2. The H2, the end equilibrium concentration, EQ. It should be the initial plus the X. And X we just solved. So the amount is 0.010 plus 0.011. That's the equilibrium concentration for the product, H2. And the units is M. This is molarity, so don't forget units. And same thing with the I2. The I2 equilibrium concentration is the initial, which is 0. Oh, okay. 0 plus X, that is X. So 0.011. X is the concentration for I2. And so you can see we have the initial concentration, and we know one of the product or reactant concentration. We can solve the entire ice table. And so we have all the concentrations. Finally, we can solve the Kc. So the Kc, based on the law of mass action, basically the product, each product raised to the power of a coefficient divided by the reactant raised to the power of the coefficient. That's how you calculate Kc, the K. For this reaction, H2, you can see H2 and I2 both are gas. So you just write down the H2 equilibrium concentration times the I2 equilibrium concentration divided by HI. The HI coefficient 2. So that should become square. Square of the equilibrium concentration for HI. And finally, you can just solve the numerical part for the equilibrium constant. Questions? Okay, any questions?
No.
I believe our homework have similar questions. Of course, it will be in the quiz. We have the ice table you can easily set up, and you'll be given one of the equilibrium concentrations. Can be either reactant or product. By solving the X, you can solve the entire ice table and then finally get to the equilibrium constant K. This slide I have answer key in the back. So